We've already seen how the LGV lemma can be used to show that every minor of the Meru Prastara or the Suchi Prastara arrays, whose entries are binomial coefficients, it can be used to show that these minors are all positive or non-negative. Now I want to show you another really cute application of the LGV lemma, and here's the matrix that I want to work with. So let's take Mn to be the matrix, n by n matrix, whose ijth entry is the GCD of Inj. We're talking about the GCD of Inj. So just to give you, make sure it's clear, let me show you what M6 looks like. So it's a 6 by 6 matrix. The first row will be GCD of 1 with 1, with 2, with 3, with 4, with 5, with 6. So the entire first row will be 1. The second row will be the GCD of 2 with 1, the GCD of 2 with 2, which is 1, 2 with 3, which is 1, 2 with 4, which is 2, 2 with 5, which is 1, 2 with 6, which is 2. Third row will be GCD of 3 with 1, which is 1, with 2 is 1, 3 with 3 is 3, 3 with 4 is 1, 3 with 5 is 1, 3 with 6 is 3. And for 4, the GCD of 4 with 1 is 1, 4 with 2 is 2, 4 with 3 is 1, 4 with 4 is 4, 4 with 5 is 1, and 4 with 6 is 2. For 5, it is just 1, 1, 1, 1, 5, 1, and for 6, it is 1, 2, 3, 2, 1, 6. So this is the matrix. And if you like, you can compute the determinant of this matrix, say using a computer, and you'll see that the determinant of this matrix is 32. These matrices, their determinants can be computed also using the LGV lemma. So let's set up a network which will compute the determinant of this matrix. So what we'll do is we'll take S to consist of 3n nodes, nodes A1 up to AN, nodes B1 up to Bn, and I'll throw in n more nodes which I'll call C1 up to Cn, and define the weights as follows. We'll define weight of AI comma Bk to be equal to phi k if k divides I. We'll define weight of Bk, no, not Bk, this should be Ck, and weight of Ck comma Bj to be 1 if k divides j, and all other weights we'll take to be 0. So I've drawn this network over here in the case of n equal to 6. So you can see that there are 18 nodes, and we have from C1 we have edges to A1, A2, A3, everything, and those are weighted phi 1. For C2 we have edges to A2, A4 and A6, and those are weighted phi 2. From C3 we have edges to A3 and A6, and those are weighted phi 3. From C4 we only have an edge to A4 weighted phi 4. From C5 to A5 phi 5, C6 to A6 phi 6. And on the other side we have the same edges, but their weights are all 1. So recall here that phi of n is the number of k such that k is co-prime to n. Alternatively, this phi n you've seen before can be defined by the relation d divides n, phi d is equal to n, and then you can use Mobius inversion to compute phi. So this is our network. Let's see what determinant it computes. So what is the number of paths from AI to Bj? What is the sum of the weights of paths from AI to Bj? So a path from AI to Bj has to go through Ck for some k, but this can only happen if k divides both I and j. So it's a sum over k divides the GCD of I and j, and the weight is phi k times 1, which is just phi k. But remember, the defining equation for this Euler-Toshin function is that the sum over all d divides n of phi d is n. So this is actually just GCD of I comma j. And so this is Mij. Therefore, by the LGV lemma, determinant of Mn is the sum over all paths omega 1, omega n, where omega I must go from Ai to Bi, and these are pairwise non-intersecting, non-crossing I should say. Product I goes from 1 to n V of omega I. In this case, the only possibility is that you have the paths that go horizontally, and so this is going to be just a product I goes from 1 to n phi of I. Now let's look at another example, this time involving the Hankel matrix of Catalan numbers. Hn is the n by n matrix whose ijth entry is the Catalan number Ci plus j. So we'll take ij going from 0 to n minus 1. So the rows and columns here will be indexed starting with 0. So for example, H3 is the Hankel matrix of Catalan numbers C0, C1, C2, C1, C2, C3, C2, C3, C4. And you can check that determinant of H3 is equal to 1. And it turns out that determinant of Hn is equal to 1 for all n. Now to set this up as an application of the LGV lemma, let's take S to be Z cross n. N stands for the non-negative integers. And let's define the weight of I comma j, I plus 1 comma j plus 1 to be 1. Northeast steps and southeast steps also have weight 1. I plus 1 comma j minus 1 to be 1. And so just to visualize this, we have here's the array, and let's take a0 to be 0 comma 0, ai in general to be minus 2i comma 0, bj to be 2j comma 0. So if you plot these points, we have a0 and b0 over here, a1, a2 and so on go off to the left, and b1, b2 and so on go off to the right. And so let's ask ourselves, what is the number of sum of the weights of paths from ai to bj? Well, each path has weight 1. It can take northeast or southeast steps, and it must be of length I plus j. So the number of paths, for example, from a path from A2 to B1 is going to have length 1, 2, 3, 4, 5, 6, which is 2 plus 1. So it's just a dig path which always stays above the x-axis, has northeast and southeast steps, starts on the x-axis and ends at the x-axis, has length 2 times I plus j. So this is just the Catalan number I plus j. And we need to check that the crossing condition holds. This is not immediately obvious, because you could have a situation like this. You could have a path which goes like this, a northeast step, and you could have a southeast path which may cross without going through any point. So this kind of a crossing is called a virtual crossing. There's no point here, there's no common point, but geometrically they cross, and so it's possible that the crossing condition doesn't hold. However, whenever this happens, you notice that if this is the point ij, this is the point I plus 1 j plus 1, this is the point I plus 1 j, and this is the point ij plus 1. If you add the coordinates of these points, these two have the same parity, and these two have the same parity. The sum of the coordinates of these two red points has the same parity, and these have the same parity. But in this, when we look at a path from AI to BJ, if a path takes a northeast step, then the parity doesn't change. Parity of the sum of the coordinates doesn't change. Same if it takes a southeast step, the parity of the sum of coordinates does not change. And here we are starting with and ending with only points with I plus j even. So this whole thing is actually not happening in the integer lattice, but in a subset of the integer lattice S prime, where I plus j in S, where I plus j is even. And there indeed the crossing condition will always hold. You cannot have this kind of a virtual crossing. And so what do we conclude? We conclude that the determinant of Hn is sum over all omega 1, well, let's call them omega 0 up to omega n minus 1 pairwise non-crossing paths omega I goes from AI to BI, weight of omega I, which is just 1. So we can just write 1. So it's just counting the number of configurations of such paths. So now let's look at this picture and let's see how we can find such paths. So there's only one path from A0 to B0, namely the path with 0 steps. Now if you have a path from A1 to B1, it has to take a northeast step. So the first step has to be northeast and the last step has to be southeast. Similarly, a path from A2 from A1 to anywhere, in fact, the first step has to be northeast and the last step has to be southeast. And a path from A2 to anywhere, the first step has to be northeast and the last step has to be southeast. So this much of the picture is completely forced. Now let's look at what we can do with the second steps. So now we have a path from here. We cannot take a southeast step because this is already taken by the path going from A0 to B0. So we have to take again a northeast step, and we get a path from A1 to B1. Now by the same token, at the next stage we have to again take a northeast step, otherwise we will have a crossing at this point A1 here, and here we have to take a southeast step, otherwise we would have a crossing at this point B1 here. And now at the next step, what can we do? Again, we cannot take a southeast step because then we'll end up crossing at this point. So we must go up, and we must go up, and we must go up, and we must go up for the same reason, otherwise we'd have a crossing at this point over here. So there's only one non-crossing configuration of paths which looks like these nested dict paths which have a single peak, and so this is just equal to 1. A similar argument can be used to compute another determinant associated to the Hankel matrix of Catalan numbers. Let's define H tilde n to be the n by n matrix whose ijth entry is Ci plus j plus 1, where ij go from 0 to n. So this is the matrix C1, C2, C2, C3, 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 C4, C4, C5. So this is, for example, H tilde 3. And again, it turns out that the determinant of this matrix is equal to 1. And let me briefly indicate how the proof works. So the setup is exactly the same, except for the choice of the points an and bn. So now we will leave alone this origin, and we will take a0 to be this point, we will take b0 to be this point. A0 is the point -1, 0, b0 is the point 1, 0. So now the paths from A0 to B0 are counted by the Catalan number C1 instead of the Catalan number C2. A1 will be, well, maybe let's extend this picture a little bit. So A1 will be over here, A2 will be over here, B1, B2. And now the only points that will be involved in these paths will be those whose coordinates add up to an odd number. Earlier it was only those coordinates, those points whose coordinates added up to an even number. And once again, you'll have exactly the same kind of situation. The only viable configuration of paths that you get will be like this. Yeah, something's wrong with this picture here. No, I seem to have crossed. Yeah, to leave a blank. And so once again, we see that det h tilde n is equal to 1 for all n greater than or equal to 1.